I'll come back with rational zero theorem. I think this might be easier to teach via the first example. Okay? List all possible rational zeros of a function. Okay? So a function has zeros, right? But there's a list of possibilities that we have to talk about because not everything is going to be factorable by our traditional methods right out of the gate. So we need to know what the possible zeros and therefore the possible factors are going to be. So in order to come up with your possible rational zeros, you look at your last term and all of its factors, which are going to be called your p's. So what are the factors of 4? 1, 2, and 4, and all the plus or minus versions of that, right? Positive 1, negative 1, positive 2, negative 2, positive 4, negative 4. So those are all the possible factors of your final term. And then your coefficient on your first term is negative 1. The factors of that are going to be considered your q's, and luckily because it's 1, we only have really 2 possible factors, plus or minus 1. Okay? So your possible rational zeros come from any combination of p over q. So your possible rational zeros come from any combination of p over q. So that's your plus or minus 1, 2, 4 over plus or minus 1. And so if I was to list these possible rational zeros, it could be 1 over 1, which is just 1. It could be 2 over 1, which is just 2. And it could be 4 over 1, which is just 4. And then any plus or minus of those. So positive 1, negative 1, positive 2, negative 2, positive 4, negative 4. Those are not all zeros of this function. But if there are going to be any rational roots, they have to be in that list. Okay? So some of those numbers will be rational zeros and some of them will not be. And the way to see whether or not they are actually rational zeros is to see if they are factors, which is where our synthetic division test would come in. So you might just start going through your list and you might test positive 1. Is positive 1 a factor of this? Now, so synthetically testing this, we have negative 1x to the 4th. How many x to the 3rds do we have? 0. How many x squareds do we have? 3. How many x's? 0. How many constants? 4. So a quick synthetic division. And we get 6. So was positive 1 a rational zero? Was it a root? No. So then you test negative 1. And your numbers are all the same, so we could just was that an actual zero? No, because we got a remainder of 6. So positive 1, negative 1 are out. Positive 2. We'll try that one. Negative 1, 0, 3, 0, 4 aren't going to change. Was that one? Yes. Okay. So here's what so we found out that 2 is an actual, one of the actual, I'll put it over here in the column, we'll say x equals 2, is 1. What is the maximum number of actual rational zeros that I might have? The maximum number I could have is 4. Now, once you find 1, now I can knock down my polynomial. It was a 4th degree polynomial, so when I divide that out, it becomes what degree of a polynomial? 3rd. So this is now negative x cubed minus 2x squared minus x minus 2. And I'm going to continue my testing from there. Does that make sense? Okay. Yes, because here's the thing. What if 2 is a double root? What if it accounts for 2 of the rational roots, right? So you've already divided it out of the original. You couldn't retest it in the original because the same thing's going to happen. So, but if you test 2 again, which you would always retest that number to see if it happens to be a double root, right? So we would test 2 again, but with these new numbers, negative 1, negative 2, negative 1, negative 2, and see if it's a double root. So we bring down our negative 1, fly through this process, and it's definitely not a double root, so that's out. So we left off with positive 2. We still have to check negative 2. Now I suppose with negative 2, you could go back to your original if you wanted to, Josh, but why? Because it's longer. So just use these newer coefficients. I don't know why I put commas in there. I did not mean to do that. And that worked. So negative 2 is also a rational zero. So I'm going to add that over here. And so these coefficients that I was using here, they came from a cubic polynomial. So when I divide out the linear factor, or the root of negative 2, that cubic polynomial got knocked down to a quadratic. So now it's just negative x squared, 0 x's, minus 1. Well, that's my quadratic. Now here's the rule though. Once you get down to a quadratic, if it's going to be factorable, you can do it by hand. 4th degree polynomials, 3rd degree polynomials, you might not be able to do by hand, but once something gets knocked down to a quadratic, we can definitely factor it the rest of the way on our own. So this one, what would we, if we were trying to solve this or factor it, we would pull out a negative. You'd be left with x squared plus 1. And is that factorable? No. So our 2 other roots, if we teed this up and solved it, our 2 other roots would be imaginary. So we do have 4 roots. 2 are real and rational. And the other 2 could have been real but irrational. Or, as we see in this problem, they are imaginary. But the actual rational roots are just 2 and negative 2. Now, I started with a fairly easy example. This is not the most efficient way to do this problem as far as coming up with the actual rational zeros, because I believe this would have been factorable by hand, right? Negative x to the 4th. I would have done negative x squared and positive x squared. And I would have done negative 4 and positive 1. Yes? Does that work? So I purposely picked one that would have been factorable by traditional methods just so you can see how it provides the same answers. X equals plus or minus 2 are 2 real and rational answers, or roots, I should say, and then this one provides our 2 imaginary roots. So I started with an example just so we could kind of self-check with what we already know how to do. But the reality is there are a lot of fourth degree polynomials out there, a lot of third degree polynomials out there that have rational roots but are not factorable by our traditional methods. So we use long division, aka synthetic division here, to quicken up that long division process to figure out what those rational zeros are to get our whole factoring process kick-started. Okay? Because like on yesterday's notes, when we were told to factor or solve, we were told to solve this. We were given a root to start with. But with this P over Q method, you do not need to be given anything anymore. Because testing your P over Q's, testing your possible rational roots until you find one, allows you to kind of kickstart this process on your own and figure out all the rational roots and all the roots, period, with or without the kickstart. You know, someone else doesn't need to give that to you anymore. So look at this problem. Our P's are going to be 1, 6, 2, and 3. Over our Q's are going to be our factors of 2, 1, and 2. So this is a longer list. Our possible rational roots are 1 over 1, which is 1, 1 over 2, which is 1/2, 6 over 1, which is 6, 6 over 2, which is 3, 2 over 1, which is 2, 2 over 2, which is 1, which some of these you'll see start to repeat, 3 over 1, which is 3, that's repetitive because we'd already done 6 over 2 and got 3, or 3 over 2, which is 3/2, and then the plus or minus of all of those. So if we are to have any rational roots, they need to fall on that list. And obviously 3 was a root. They told us that. So if we were just randomly testing, you kind of are just guessing and checking, you would eventually get to 3, find out that it's a root, knocks it down to a quadratic, and the rest you can then do by hand. So the other rational roots we got, the other 2 roots that we got once we did our quadratic by hand, were 1/2 and -2. So those are 2 additional real and rational roots, and sure enough, they both are on our list. Okay? Because this is a list of all possible rational roots. Like I said, some of them are real roots, are actual roots, and the rest are not. But you have to kind of sift through via synthetic to find out what they are. Josh? Right, yeah, no, they are. I didn't write that. So I said that. I said we would get them, all those combinations, and then you have to test the positive or negative of them. So it can obviously become a very robust problem because there's even just here how many to check. Then double it because you've got the negative version of all of them. So it becomes large, but it's just to kind of illustrate to you that there is a way to factor things being told nothing at all. Okay? Not efficient, not an efficient method, but there is a way. Okay? Questions? So now if we go back up to this theorem, just now it will make more sense. Before it would have been all symbols, wouldn't have made much sense. So here's a polynomial. If you have f of x, no matter what the degree, so to some nth power and then all the terms in between until you get down to plus some constant b, p are all your factors of b, and q are all your factors of a, then all the possible rational zeros are given by any valid integer combination of p's over q's. Okay? So, again, that's your list of possibles, and only 1 or 2 or 3 of them from your list will actually be zeros. Is that clear? Okay. So we continue kind of looking at this problem. How many roots should the function have? 4, because degree of 4. And find all of the roots, which we've got 2 of them, x equals 2 and -2. And then once we were down to this quadratic, we can solve for the other 2 roots by hand. So if we tee this up and set x squared plus 1 equal to 0, subtract 1 from both sides, x squared equals negative 1. Square root both sides, and the two other roots are what? Plus or minus I. Very good. And you see here, obviously, just to remind you that conjugate or imaginary roots always come in pairs of conjugates, right? So that's like 0 plus I and 0 minus I. Those are conjugates. Imaginary roots always come in pairs of conjugates. Okay? Do you remember that from last year? All right. Solve. This one is not factorable by hand, by our, I'll say, by our traditional methods of grouping. Now I've put an example on here that is not going to work, okay? So if we look at our list of possible ones to check, our P's are 1, 24, 2, 12, 3, 8, 4, and 6. Our Q values are just 1. The factors of 1 are just 1. And then all the plus or minus versions of that. Okay? Just out of curiosity. Obviously, you saw we can test all of these with synthetic division, which is, you know, the reason for that skill and being able to do it so fast. How else could you test to see if and which of these numbers are roots? Taylor? Meaning what? Right, so that's not even really the remainder theorem. If you plug something in and you get 0, then you know it's a root, right? What we're doing with synthetic division is actually the remainder theorem, right? We're looking at the remainder. If it's 0, then we know it's a root. That's the remainder theorem. Just finding a root is something that when you plug it in should get it equal to 0, right? The problem is without a calculator, if you tried to plug in 24,
or without a lot of time.
Right. If you tried to plug in 24 to the 4th power, you would be, you know, out of luck. So, we can do some of them in our head, though. Like if we tried positive 1, we would get 1 minus 6, that's negative 5. Negative 5 minus 8 is negative 13. Negative 13 plus 24, does that equal 0? Okay, so I'm going to keep kind of a tally of what we've checked. How about negative 1? Negative 1, again, so I would say sometimes when you're plugging it in, it makes you a little bit more nervous that you're going to make a mistake because you're doing it in your head. But obviously it can be done, whatever you're comfortable with, or we can do synthetic division with negative 1. So I'll just do a round of synthetic with negative 1. So I have 1x to the 4th, 0x cubed, negative 6x squared, negative 8, and 24. And if I run through that real quick, that doesn't work. So 1 and negative 1 are out. I'm going to stay away from 24 until later. I'd prefer to start with easier numbers. So maybe I'd try 2 next. 2. It's not? You're right. Sometimes the denominator changes it, but we're lucky in the case of a denominator of 1 that we don't have to worry about that. That was a bingo. That one worked. Yes? So 2 worked. And it knocks our polynomial down to, it was a 4th degree. I'm going to circle that. It was a fourth degree, so it knocks it down to a cube. So x cubed plus 2x squared minus 2x minus 12. Does that make sense? And then what number do we test next? Nope. 2 again, in case it's a double root. Otherwise, you're going to miss it. And then you'd really be thrown off because you'd be like, why doesn't anything else work? Now, it's not common that it's a double root, but it can definitely, you've seen plenty of double roots. But now I'm going to use these new cubic coefficients. 1, 2, negative 2, and negative 12, because it just shrinks up my problem by one step. Guess what? It was a double root. So 2 worked twice. And then now my cubic polynomial gets knocked down to a quadratic. So x squared plus 4x plus 6. And I can definitely try to factor this by hand. So we're left with this equaling 0. Is it factorable? No. How would you solve it? Because we have 2 solutions so far, and we need 4. So if it's not factorable, we're going to solve it by quadratic formula. Negative b squared minus 4 times a times c all over 2. (16 minus 24, negative 8, all over 2. Negative 4 plus or minus 2i root 2. And then we can reduce that by 2, negative 2 plus or minus I root 2. So we have our 4 solutions. 2 real ones, happens to be the same solution twice. So x equals 2. And negative 2 plus or minus I root 2. There's our imaginary roots coming in pairs of conjugates again. Good? So I tend to try to avoid testing larger numbers until the end. Like I skipped 24, not because I knew 2 was going to work, just because I genuinely don't want to try 24 unless I absolutely have to. Okay? What are our P's? Kendall? I'll just put a plus or minus out in front. 1 and 3, good. And our Q's? Jalen? Just 1, good. So the only numbers I have to check are 1 over 1, which is 1, so positive 1 and negative 1. And then 3 over 1, which is positive 3 or negative 3. I could do 1 in my, without synthetic. 1 cubed plus 7 times 1 squared is going to give me 8. 8 plus 11 is 19. 19 minus 3, so does positive 1 work? No. I could also test negative 1. Just doing f of negative 1, I get negative 1 plus 7 gives me 6. 6 minus 11 gives me negative 5 minus 3. Does negative 1 work? No. Does everyone see what I'm doing there? I know I can't really track it because I'm doing it in my head, or I could write it down, but that would be a lot. So 3, can we try 3 in our head? 3 cubed is 27 plus 3 squared is 9. 9 times 7 is 63. 27 plus 63 is 90, right? 90 plus 33, this is not going to work, right? And then try negative 3. I'm going to synthetic with that because I don't trust myself. 1, 7, 11, negative 3. And of course it works. Synthetic is just much less thinking. So if you don't want to try plugging things in and doing mental math, then just do a boatload of synthetics. Synthetic is obviously more writing, less thinking. The other is more thinking, less writing. But you pick your poison, because obviously the more thinking in your head can cause more mistakes. So immediately x cubed gets knocked down to an x squared. So we have 1x squared plus 4x plus 1. And we want to find the roots of that. So we have 1, 0 at negative 3. And our other two are going to come from solving the quadratic. Is it factorable? Unfortunately, no. So again, the quadratic formula. Do we follow? Can we jump to the last one? Yeah. Oh, yeah. You're absolutely right. Good catch. Negative 3, negative 1 gives me 3. So it still works. It just would have screwed up this. And then it would have screwed up my other two roots. Kendall? Negative 3 might be a double root. It could be. But if I get it down to a quadratic, you can just take the quadratic to the end based on how you know. Okay? To keep going with synthetic division seems a little bit like why guess and check when you don't have to. We have to guess and check from the start because this is not factorable by hand. Any quadratic is factorable or solvable by hand. Anything else? That was a good question. And the last one, P's and Q's. Our P's are 1, 6, 2, and 3. Our Q's are just 1. You want me to finish it? While I'm doing the last problem, I want you guys to try to find something that works down here. There, Josh. There's your three roots. Negative 3, and then negative 2 plus or minus root 5. Did you get that? Does anybody have anything that definitely works on the last one so I can save myself the guessing? 2. Oh, good. So here's what's funny. If Josh finds 2 first and divides that out, the quadratic he's left with is going to be different from what Taylor gets. Because when she divides her number out, she's going to get a different quadratic than Josh got. But then when they factor their respective quadratics, their 3 final factors should be the same thing. So the fact that they both got 1 and they got 2 different ones tells me that these are going to be 3 rational zeros. Because they're both going to have a quadratic that is definitely further factorable into what the other one got and then a third factor. So if I take out 2, you said, Josh? Well, I'm about to tell you. Yep. So he gets x squared plus 4x plus 3, which factors into x plus 3, x plus 1, and then obviously the x minus 2. Whereas Taylor got, which one did you get first? The negative 1? Right, so you got the negative 1 first. You factored, you pulled that one out, and then your remaining quadratic factored into these 2, right? So the order in which you get your 3 factors is just different. Your solutions are all the same. Good stuff? Whole new world out there you never knew about. And I bet you're glad you didn't know about it.